On paper, the Bombardier ALP-46A was fully compliant. Every clearance met the published standards. Axle loads fell within approved limits. Pantograph height and reach passed inspection without issue. Standing still at a platform, this locomotive satisfied every requirement the Federal Railroad Administration had on file. Then it started moving, and what happened next revealed something that decades of American railroad regulation had never properly accounted for: the difference between a machine at rest and a machine in motion. This is the story of a locomotive that didn't break any rules. It simply exposed that the rules themselves were incomplete. By the mid-1990s, New Jersey Transit faced a fleet crisis. Their electric locomotives, primarily EMD ALP-44s, were approaching the end of serviceable life. The electrified portions of their commuter network demanded reliable, high-performance equipment, capable of intense acceleration and frequent stops. Commuter rail service places unique demands on motive power. Unlike freight operations, where sustained pulling force matters most, or intercity service, where top speed is paramount, commuter duty requires rapid acceleration from station stops, schedule maintenance through dense traffic, and doing this dozens of times per day, 7 days a week. Motors heat and cool constantly. Traction systems engage and disengage at rates that freight locomotives might experience over an entire week, compressed into a single morning rush. American locomotive manufacturing had, by this point, largely consolidated around diesel-electric designs. Domestic expertise in pure electric locomotives had diminished considerably since the Penn Central era. NJ Transit's engineering staff became interested in what European manufacturers had developed. The European rail market operated under fundamentally different conditions: dense population corridors, high electricity costs favoring efficient power conversion, and decades of continuous investment in electric traction had produced impressive equipment. Germany's Deutsche Bahn Class 1001, in particular, seemed ideally suited to commuter service. A proven high-speed locomotive capable of 220 kilometers per hour, with a reputation for reliability and sophisticated electronic controls. Bombardier Transportation offered a design derived from the Class 101. Adaptation for American service required substantial modification. American loading gauge differs from European standards. Coupler heights, cab configurations, and numerous details needed redesign. But the fundamental architecture would carry over: 6-axle arrangement, 3-phase AC traction motors, modern IGBT-based power electronics. NJ Transit placed an initial order in 2001, with the first units arriving in 2002. The assumption underlying this procurement seemed reasonable. If the locomotive met American regulatory requirements as measured by established testing protocols, it would perform acceptably in American service. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. The Federal Railroad Administration's equipment standards evolved from practices established in the steam era and refined during dieselization. These standards addressed what could be measured reliably with available technology: static dimensions, weights at rest, structural strength under standardized test loads. When a locomotive arrived for certification, inspectors measured height, width, and length against published clearance diagrams. They weighed the locomotive and calculated axle loads. They inspected the pantograph mechanism, confirming it could reach the contact wire at specified heights. All measurements occurred with the locomotive stationary. This approach made practical sense for decades. Early diesel locomotives used relatively simple suspension systems. A locomotive that measured properly at rest would remain within those measurements while moving, plus or minus a small margin that clearance standards already accommodated. The loading gauge diagrams included dynamic envelope allowances, additional clearance margins, accounting for the fact that trains sway slightly as they move, suspension systems compress and extend, and curves cause vehicle ends to swing outward. But these allowances were based on equipment behavior observed over generations. The calculations assumed a certain range of suspension characteristics, a certain pattern of oscillation frequencies, a certain relationship between speed and lateral movement. Older American electric locomotives, the GG1s, E60s, and ALP-44s, behaved in ways these traditional allowances accommodated well. Their suspension systems used technology dating back decades. their mass distributed in familiar patterns. They interacted with track and catenary in ways railroad infrastructure had evolved to handle. The engineering sophistication that made the ALP-46A attractive to NJ Transit also made it behave differently from anything American catenary infrastructure had previously encountered. Modern European locomotive design incorporates what engineers call active or semi-active suspension management. The goal is to optimize ride quality, reduce track forces, and allow higher operating speeds. These systems permit the locomotive body to move relative to its trucks in complex ways, following track irregularities rather than fighting them, damping oscillations that might otherwise build to problematic levels. This represents genuinely advanced engineering, but it also means the locomotive exhibits dynamic behavior different from passively suspended equipment. When an ALP-46A accelerates, vertical forces act through its suspension system in patterns that static measurement cannot capture. The locomotive body rises and falls relative to its trucks. This vertical oscillation occurs at frequencies determined by the suspension tuning, and those frequencies may or may not match the natural frequencies of the infrastructure the locomotive operates over. Lateral movement presents similar considerations. The trucks shift slightly side to side as they follow track imperfections. At certain speeds on certain track geometries, these lateral movements can approach the limits of the dynamic envelope more closely than older equipment did, not exceeding the envelope necessarily, but operating nearer to its boundaries. The pantograph situation proved most consequential. A pantograph appears simple, a folding arm mechanism that holds a contact strip against the overhead wire, collecting current to power the locomotive. In reality, pantograph catenary interaction involves complex dynamics that rail engineers have studied intensively. The catenary system, the overhead wire arrangement that delivers power to electric trains, has physical properties that vary along its length. Where the contact wire is supported by hangers attached to a messenger wire above, the system is relatively stiff. Between supports, the contact wire can move more freely. At locations where sections of wire are joined or where geometry changes occur, the characteristics change again. As a pantograph passes along the wire, it exerts an upward force. This force must be sufficient to maintain good electrical contact, but not so great that it lifts the wire excessively. If the wire rises too much, it creates a wave that propagates along the catenary. At certain speeds, these waves can interact destructively with the passing pantograph, causing loss of contact, arcing, and accelerated wear. The ALP-46A's pantograph system was designed for German catenary. Deutsche Bahn's overhead lines use higher tensions, different support spacing, and different geometries than American installations. The European system is tuned to support higher speeds and permits different pantograph force characteristics. American catenary, particularly on the Northeast Corridor and NJ Transit's electrified territory, represents multiple generations of installation and modification. Some sections date to the original Pennsylvania Railroad electrification of the 1930s. Others reflect upgrades made at various points over the following decades. The result is a system with varying stiffness, varying tension, and varying geometric characteristics along its length. When the ALP-46A operated over this mixed infrastructure at speed, its pantograph interacted with the catenary in ways that differed from the locomotives the system had been designed around. The contact force characteristics, the frequency of the pantograph head's vertical movement, the relationship between speed and wire uplift, all these parameters fell outside the envelope that American catenary had evolved to accommodate. This was not a failure of the locomotive. The ALP-46A performed exactly as designed. Its pantograph maintained contact within the specifications Bombardier had established. The problem was that those specifications assumed infrastructure characteristics different from what existed in American territory. The Northeast Corridor electrification represents one of the oldest continually operated electric railway systems in North America. The original Pennsylvania Railroad installation, completed in the 1930s, used design practices appropriate to equipment of that era. Subsequent modifications addressed specific problems and incorporated newer technology, but fundamental system characteristics retain legacy properties. Catenary stiffness varies significantly along the corridor. Where support structures are closely spaced, stiffness is high. Where spans are longer or older hardware remains, the system behaves differently. Temperature affects wire tension, causing seasonal variations. Track curvature influences how pantographs track across the wire surface. When the ALP-46A entered service, maintenance personnel began observing unfamiliar patterns. Contact wire wear appeared in locations and at rates different from historical experience. The wear patterns suggested something about this locomotive's interaction with infrastructure differed from established norms. This was not dramatic damage. The catenary continued functioning, service continued operating, but maintenance data indicated infrastructure originally designed around older locomotives was experiencing forces outside its design assumptions. Similar observations occurred regarding clearances. The ALP-46A passed through tunnels and past platforms with dimensions meeting standards. But dynamic envelope utilization, how closely the locomotive approached the theoretical clearance limits while moving, differed from older equipment. On certain curves, at certain speeds, margins between the moving locomotive and fixed structures were smaller than anyone had seen before. Nothing exceeded published limits. The locomotive remained within legal clearances, but the assumptions embedded in those limits, developed through decades of experience with different equipment, did not account for this machine's behavior. The operational response to the ALP-46A's behavior emerged gradually and without drama. This was not a crisis requiring emergency action. It was an engineering situation requiring methodical analysis and appropriate operational adjustments. NJ Transit and Amtrak, which manages the Northeast Corridor infrastructure, began implementing speed restrictions in specific locations. These restrictions were not applied uniformly to the ALP-46A throughout its operating territory. Rather, they addressed particular zones where the interaction between the locomotive's dynamic behavior and infrastructure characteristics produced effects outside acceptable parameters. Sections of catenary with certain stiffness characteristics received attention. Locations where clearances were tightest became subject to lower speed limits. The restrictions reflected engineering judgment about where the margins were insufficient for this particular locomotive operating at full line speed. From outside the railroad industry, these restrictions appeared puzzling. The locomotive had been certified. It met all published requirements. Why was it suddenly unable to operate normally? The answer lay in the gap between static certification and dynamic reality. The ALP-46A had never been illegal. It had never failed to meet any requirement actually imposed upon it. What happened instead was that service experience revealed requirements that should have existed but did not. The regulatory framework had assumed that static compliance implied dynamic compatibility. The ALP-46A demonstrated that this assumption was not universally valid. A locomotive could meet every published standard and still interact with infrastructure in ways those standards had not anticipated. This represented a failure of the regulatory system, not of the locomotive or its manufacturer or its operator. Bombardier delivered equipment that met specifications. NJ Transit purchased equipment that satisfied requirements. The infrastructure owners maintained their systems to establish standards. Everyone involved had acted properly within the existing framework. The framework itself was incomplete. The ALP-46A experience was not entirely unique, though its specifics were distinctive. American railroads had encountered similar situations throughout the history of electric traction, though rarely so clearly documented. When the Pennsylvania Railroad introduced the GG1 in the 1930s, that locomotive represented a dramatic advance over previous electric power. Its articulated design, with two powered truck assemblies sharing a common frame, produced dynamic characteristics different from earlier rigid frame equipment. The railroad adjusted operating practices and, over time, infrastructure characteristics evolved to accommodate the GG1's behavior. The same pattern occurred with the Metroliner equipment in the 1960s and with subsequent high-speed developments. Each new generation of equipment brought dynamic characteristics that differed from predecessors. Each required some period of adjustment, during which operators and infrastructure managers learned how the new equipment actually behaved in service. What distinguished the ALP-46A situation was the clarity with which it illustrated the static dynamic compliance gap. Previous generations had made this transition more gradually, with less obvious distinction between certified parameters and operational behavior. The ALP-46A's sophisticated suspension and its pantograph characteristics, optimized for European conditions, made the distinction impossible to ignore. Following the ALP-46A experience and similar situations with other equipment, the Federal Railroad Administration revised its certification. Approach: dynamic testing requirements expanded. New equipment would be evaluated not merely for static compliance, but for actual behavior at operating speeds. Simulation tools allowed regulators to model vehicle infrastructure interactions before equipment entered service. The concept of infrastructure compatibility emerged as a distinct regulatory concern. A locomotive could be perfectly satisfactory equipment and still be incompatible with specific infrastructure. The regulatory framework needed to address this interaction, not merely certify individual components. European practice had evolved differently. The concept of system compatibility, treating vehicle and infrastructure as an integrated whole requiring matched characteristics, was deeply embedded in European regulatory philosophy. High-speed rail developments of the 1980s and 1990s had reinforced this approach. The ALP-46A forced American regulators to recognize that imported equipment brought European assumptions, along with European engineering. A certification process built around American assumptions could approve equipment that would not perform as expected. Despite the operational restrictions, the ALP-46A fleet has provided effective service for New Jersey Transit. The locomotives handle heavy commuter consists with the acceleration performance their procurement sought. Reliability has been generally satisfactory. The concerns about dynamic behavior, while real, affected specific operating conditions rather than wholesale locomotive capability. The restrictions remained in place because the underlying infrastructure characteristics did not change. The catenary sections with problematic interaction characteristics were the catenary sections that existed. Rebuilding them to different specifications would have been enormously expensive and disruptive. Operating the ALP-46A at reduced speeds in those sections was a more practical solution. This represents a common pattern in railroad operations. Infrastructure changes slowly, measured in decades rather than years. Equipment turns over more rapidly but must accommodate whatever infrastructure exists. Operational adjustments, speed restrictions, route limitations, and maintenance intervals bridge the gap between ideal system design and practical reality. The ALP-46A fleet has continued in service through the 2010s and 2020s. The locomotives have been supplemented by additional units and, eventually, will be replaced by successor equipment. When that replacement arrives, the certification process will incorporate lessons learned from the ALP-46A experience. Dynamic behavior will be evaluated before equipment enters service. Infrastructure compatibility will be considered from the beginning. The ALP-46A case has become something of a teaching example in railroad engineering circles. It illustrates several principles that apply far beyond this specific locomotive. First, certification is not comprehension. A certificate indicates that measured parameters fall within specified limits. It does not indicate that all relevant parameters have been measured or that the specified limits capture all meaningful constraints. The certificate represents the state of regulatory knowledge at the time it was issued, nothing more. Second, proven performance elsewhere does not guarantee comparable performance here. The Class 101 was entirely successful in Germany. The ALP-46A is derived from the Class 101. The ALP-46A did not replicate Class 101 performance in America because America is not Germany. Infrastructure differs. Operating conditions differ. The assumption that equipment will behave similarly in different environments must be validated, not assumed. Third, dynamic behavior can differ categorically from static behavior. A suspended system, whether a locomotive or any other mechanical assembly, behaves differently in motion than at rest. This is not a subtle effect or a minor complication. It is a fundamental characteristic of physical systems. Any certification process that ignores dynamic behavior is necessarily incomplete. These principles apply to railroad equipment procurement worldwide. They apply, with modification, to many other engineering domains where certified components must operate within systems designed around different assumptions. The ALP-46A was fully legal on paper, but reality exposed what the rules failed to ask. Compliance at rest didn't guarantee understanding in motion, and physics made that clear.